Okay, so we welcome to the second day for this reinforcement learning session. Okay, so we will continue from where we stopped yesterday. So this will be continuation, and towards the end we can see some practical. So I'll show some code and I will execute the code. You'll see this policy iteration algorithm. That is the basic algorithm in reinforcement learning, and I'll show the execution also, so that you have some idea of how the things work as a code. Okay. So you can stop me by just asking question or typing it in the message, okay, the chat message. Okay, so I think the slides are visible. So, okay. So let's get started with the slides. Okay. So our final goal today is to learn about the policy iteration algorithm and to see the implementation of the policy iteration algorithm in Python. So Python is commonly used for many reinforcement learning algorithms. But the limitation with Python is it may be sometimes slower. The code may take longer time to run, but it is much easier to code since there are a lot of libraries already available. It's more easier to code. Okay, so yesterday we were talking about multi-arm bandits, and we started with the reinforcement learning. So I was talking about states, agent, and environment, how to divide, how to separate the agent from the environment, and what are the states, what are the actions, then rewards, and then the model. The model has the translation probability and how the rewards are given. So now let's look at what is called as return. The term return here means how to accumulate a reward, how you accumulate the reward, that is termed as return. So how do you accumulate rewards? You get rewards at all the time steps. When you perform an action at a particular state, you get a reward, say RT. At time step T, you get a reward RT. Okay. So let us denote the sequence of reward received after the time step T by RT plus 1, RT plus 2, and so on. Okay. This is starting from T plus 1, you go on, okay, for all the future time steps. So if you recall, yesterday we had seen for a multi-arm bandit, we had something termed as QT of A. Okay. That was an estimate of the mean return of a particular arm. So that we calculated using incremental update. That is in some ways your return in your multi-arm bandit. Here it is more complicated because you have states. There was no states, or you can say there is only one state. But here there are different states, and rewards also depend on the state and the action. Now there is a term called GT. The term GT is the expected return. So the term return is used to denote the accumulated reward. So first we assume that we are having only finite time horizon. So the finite time horizon means you count start from time t, small t plus 1, you go on till the final, there will be a final time step, capital T. You sum all the rewards till capital T. That if you start from RT plus 1 and go on to the last time step, capital T, all the rewards you sum will be finite because this T is a finite number. So all these rewards are numbers. So if you add it, you will get another number. It will be bounded, and this will be a finite sum. Okay. So this term is called GT, which is this is a random quantity, because RT is, the rewards are not deterministic, they are probabilistic, stochastic. So they can change for the same state and same action. You may get different rewards at different times, different points. It is the same action, same state, but you may get different reward once and may get different reward second time, because the rewards are stochastic. So all these are stochastic. So this GT quantity is a random variable. So it is not an deterministic thing. It is a random quantity, and this is called expected return. And what we are looking for is, we are trying to maximize this return. So this is the return. GT is the return. So what we want to do is maximize the expected return. We'll look at what is the expected return, and then we'll see how to maximize the expected return. So in the simplest case, this is the return. This is not the expected return. This is the return, which is a random quantity. It's a random variable. So this approach has one assumption. The assumption is there is a final time step. So this is useful in many. This is the case with many examples. So you have what is called as episodes. So after, for example, in a game, chess game or Go game, the game will end, right? So you play, you keep making moves, you keep receiving rewards, and it will end after a particular time step. So these are called, there's a final time step. These are called episodic tasks. So this is what is given here. So when the agent interaction breaks into subsequences, these are called as episodes. Then the end of the episode is denoted by the capital T, and after that it restarts again. You restart the state again and again start from 1 or 0, and then go to capital T again. Okay. For example, not all applications are episodic. There are applications in which these episodes are not there. So in such an application, you call it non-episodic. It is called infinite horizon. These are called finite horizon. For example, of finite horizon is a game, place of game, or if you have a maze, a trips to a maze, or any sort of repeated interaction. These are examples of episodic task. So there you have a final time step, a capital T. These are finite horizon problems. So each episode ends in a special state, which is called the terminal state. So that is the ST. Okay, the RT, you get the reward RT. So you go to a state ST. ST is the terminal state. After that, what happens is you restart. You restart and go to some random starting state. Okay, it may be some fixed starting state or maybe any random starting state. These type of tasks are called episodic tasks because they have some repeated resetting. So you reach a final state and again you reset. Okay. There are other examples of tasks which do not break into episodes, but it goes on continually without any terminal or end. These are called as infinite horizon or non-episodic tasks. A typical example will be any control task. For example, if you say that there is a robotic control, or if you say autonomous driving, these are examples of continual process control, continual control task. And in this setup, we will not have a capital T. The capital T will be equal to infinity. Okay. So in this case, you cannot have the sum because the sum will be infinite. Okay, you cannot add all the rewards till infinity. What we do in that case is we multiply the reward with the discount factor, and the discount factor will be multiplied at each time step. We'll see that. That is called discounted reward. In that case, the sum will converge. Or another way to do the infinite horizon is you take the average. I consider the average reward. That will not be infinity. That will be a finite quantity. Okay. So it is this is the first way. So the first idea is use of discounting, and today the example we will see towards the end of this lecture, policy iteration, will have a task which is infinite horizon and which will use discounting. There will be a discount factor. Okay. So in this discounting approach for infinite horizon, what you do is you discount the reward at future time step. Look at this equation. So this is not very clear, but I think I'll highlight this. This is a summation. It's not cross, it's a summation. So it is clear in the PDF, but this PPT is not clear. So this is in summation. Okay. So you have the reward RT plus 1, same as the finite horizon. Then look at this, you have gamma times RT plus 2. This is extra. So this was not there in this previous equation. This equation did not have that. In this you have gamma, and the second term will have gamma squared. The third term will have gamma cube, okay, and so on. So this is an same notation. This is same as this. So you write it as a summation 0 to infinity. So here gamma is the term is called discount factor. It's a parameter. It normally lies between 0 and 1. This is called discount rate or discount factor. So normally if it is 1, it will not converge. So it should be strictly less than 1 for convergence to happen. So why is this done? The reason is there is an intuition behind this. So you give more weightage to immediate past than to distant past. So immediately you give more importance, and eventually what happens, you give lesser importance. So the discount rate determines the present value of future rewards. Okay. A reward which is received k time steps in future is worth only gamma k power 1 times what it would be worth immediately. Okay. So if you get a reward, say some reward X, or let's say R in the future, okay, that is at that time step. That future reward will be worth much less before. So before it is received, you will give it lesser weightage. So what the idea here is, you give more weightage to immediate rewards and less weightage to future rewards. So some reward which is distant in the future, you will give much less weightage. So that is the idea, and this is quite commonly used in infinite horizon reinforcement learning. Okay. If gamma is less than 1, this is normally a constant. It is not changed. Gamma is a constant. So gamma is less than 1. This will converge. So these are numbers. So gamma is less than 1. You can show that this infinite sum will be bounded. Will be a number. And if gamma is equal to 0, if I say gamma is 0, okay, I can set gamma to be 0 also. In that case, GT will be equal to RT plus 1. That is, you consider only the immediate reward. If you give high value of gamma, that means you give more weightage to future rewards. If you give less value of gamma, you will give, it is like you are giving more weightage to immediate rewards. Okay. So if gamma is equal to 0, the agent is in some ways myopic, and it is looking only at immediate future, not a distant future. And it is concerned only with maximizing immediate rewards. The objective in this case is just you choose an AB which maximizes only RT plus 1. Okay. Because in this case, you will consider only RT. GT will be equal to RT plus 1. Okay. So if you find the action which maximizes GT, it is like maximizing RT plus 1. Okay. And as gamma approaches 1, more and more close to 1, future rewards are also considered. Okay. And if it is very close to 1, they are bound more strongly, and the agent becomes more far-sighted. So normally this gamma value is close to 1. It is set as 9.95, 0.98, 0.99. It is not having, normally it does not have a low value. In practical thing, you can normally set it very close to 1, so that the agent looks also at the future. So sometimes you have something called a unified view of both episodic and non-episodic task. So so you can have, so this is summation again here. So in this case, you can look, so you can set gamma equal to 1 and some finite t, or t equal to infinity and gamma between 0 and strictly less than 1. So you can have a term which generalizes both episodic and non-episodic task. Okay. So it is the same thing as before, what we saw before, this one and this one. We are writing it as the same expression, which will include both the two cases. It includes the possibility that t equal to infinity, that is, you have infinite horizon, or gamma equal to 1, which will be finite horizon. And in infinite horizon, gamma will be less than 1 and greater than or equal to 0. Okay, so let's continue. Now, we have just seen accumulating rewards, the returns. Now we have to go to the important part called Markov property. So I had mentioned what is something called as Markov decision process last lecture. Yesterday we had seen that. I had mentioned Markov decision process. So what is the Markov there? So Markov is the name of a person. So there is a probabilist. So the name is used for a particular property. There is something called a Markov property. We'll see what is this Markov property. And then there is something called as control Markov property, which is there, which is what has to satisfy for a Markov decision process. Okay. We'll see that. To understand Markov decision process, you should know what is a Markov property. And if you want to model your problem, you have some problem, you want to use reinforcement learning algorithm for that. One thing you have to check is the Markov property. Does the Markov property hold? Okay. So the basic concept is intuitive. There is also some mathematics probability involved. It's not difficult, but there is, to define it, you need some conditional concepts of conditional probability. We'll see that. So before that, you recall that in an RL framework, the agent makes its decision as a function of the signal from the environment called just the environment state. So the action of an agent depends on the state. Okay. So we have seen this as policy. So policy was a mapping between the state space to the action space. Suppose I am in state S10, what will be the action I will take? If I am in state S2, what will be the actions I will take? So this can also be probabilistic. So this I have mentioned in the previous lecture. Okay. So what we do is we assume that the state is given by some, it's not part of the agent, it is given by the environment, some processing system which is normally part of the environment. It is not just normally, it's you can even say it is always part of the environment. So we will, when we are looking at designing algorithms, we will not focus on designing, modeling the problem or designing the rewards. These are different. So designing algorithms, RL algorithms for a general task is different. Modeling a problem is RL problem, and designing rewards for that problem to solve, to get to a particular goal is different. They are two different things. What we will be focusing is on the more difficult, more general task, not on the designing, modeling a problem or going into reward designing. So we will not focus on designing state signals, or we will not worry about designing rewards. So the state signal should be immediate measurements, in the sense that if you are at state, if at time step t, if you are at some state, it should be immediately known. The state at time t should be known at time t. It should not happen that at time t, the state at time t is not only at time t plus k. That cannot happen. So at that time, you should know what is the state. That's what is meant by immediate measurements. So these are some other assumptions. So state signals should not be expected to inform the agent of everything about the environment, or even everything that would be useful in making decisions. Okay. So it can only give partial information about the environment. So there could also be something called as hidden state, something like hidden state information. These are called as partially observable Markov decision process, POM-DPs. So this is a slightly different topic. So so the state need not be also fully known to the agent. Sometimes only partially it may be known to the agent. So it may have some hidden, there may be a hidden component to the state. So even this can be taken into account. Some more general form of an MDP called partially observable Markov decision process. So we will also like to have, generally this is what we like to have, a state signal which summarizes all the past in some compact way, yet in some ways it only has the relevant information. This is what normally we expect the state signal to convey. Okay. This is what is important. What is a Markov property? A state signal that succeeds in retaining all the relevant information is said to be Markov or Markov property if this this equation. So we'll come to this equation in the next slide. So if a particular equation holds, okay, we'll see what is this equation. Before that, we have to get into some notations. So these are standard in reinforcement learning, and you have to be comfortable with them. So you cannot follow any reinforcement algorithm without these notations. Mostly these are standard. So no matter what book you see or what papers you see, these notations will more or less be standard. First, assume there are finite number of states and finite reward values. In general, it is not necessary, but for simplicity, we assume this. Consider how the environment might respond at t plus 1. What is the state at t plus 1? When the action, some action AT is taken at time step t. Okay. So the environment responds by two things. One is the reward, and one is the state. Okay. So this is the reward at time step t plus 1. This is the state at time t plus 1. Okay. This is what is the model or the dynamics of the problem. Okay, this is determined. This is defined by a probability distribution. Look at this. So what is the reward I get at time t plus 1, and what is the state I am at time t plus 1? This is conditional probability given. So these two given the entire history. State at 0, action at 0, reward at 1, and state at 1, action at 1, reward at 2, till state at t and action at t. Okay. The reward at t plus 1 is what the environment gives, and state at t plus 1. Okay. So this r, small r, and s prime can take any value with this finite number of states and finite number of reward values. Okay. The small r and small s. So this is a probability distribution. Given the entire history, first state, first action, first reward till T state, T action, the entire history, what is the T plus first reward and what is the T plus first state. Okay. Probability that what is the T plus first reward and what is the T plus first state. Now we see what is a Markov property. This is the important part. So Markov property says exactly this. If the state at T plus 1 and reward at T plus 1 depends only on state and action at T and not on the past. If you are given the state and action at T, it is independent of everything before that. If that is the case, it's called Markov. It satisfies the Markov property. That's what is given here. So if the environment's response, that is, what is the state, next and next reward, it depends only on the state and action at T. If at T plus 1, the response depends only on the state and action at T, then you say that it satisfies the Markov property. In that case, you will say RT plus 1 equal to R, ST plus 1 equal to S prime, given ST and AT, not the entire history from 0. Okay. You just consider the current state, what is the next reward and what is the next state. So a state signal has the Markov property, okay, and is a Markov state only if this is equal to the entire history. So if you are given the entire history, what is the probability of RT plus 1 equal to R and ST plus 1 equal to S prime is just this equation. Okay. If this is the case, then you satisfy the Markov property. And this is necessary for modeling any problem. You have to see if this is the case. Mostly it will be the case. To say it in language, English language, so it says just that the future is independent of the past given the present. Okay. You may have seen Markov chains in mathematics and probability. It's a very similar concept. The only thing difference here is you also have action. There you will not have action. In Markov chains, you only have states. Here you also have actions and also you have states and also reward. Okay. Sometimes we say the environment or the task itself, the problem itself has the Markov property. You have to check this Markov property, that is the future is independent of the past given the present. You have to check this before using any RLM method. What is useful with this Markov property, then the advantage is only one-step dynamics are enough. If you know this, that is enough. You don't have to know the entire history. Okay. So it's much easier if the Markov property is satisfied. Only one-step dynamics will be sufficient, will suffice. By iterating the same equation, we can say that we will predict all the future states and expected rewards from the knowledge of only the current state. And what about the policy? The best policy for choosing actions as a function of a Markov state. So when you are trying to find the optimal policy, you just have to look at the one-step dynamics. You don't have to look at the entire complete history. So the policy need not depend on the entire history. Suppose I want to take an action at time step t, it does not have to depend on the past. You can show that for a Markov, if the Markov property is satisfied, then the policy has to depend only on the current state. It does not have to depend on the previous history. So that's what is given here. So a function of the Markov state is as good as best policy, using it as a function of complete history. So you don't have to worry about the entire history. The policy can depend only on the state, current state. What is the action need would only depend on the current state. Even when it is non-Markov, so most of the problems are Markov, But even if it is non-Markov, you can think of some approximation to Markov and you can try to use some R algorithms. This property is quite important because the decisions and values are assumed to be functions of only the current state. So it simplifies a lot of things in algorithms and in theory also. And this is the fundamental assumption in reinforcement learning. This is about the Markov property. Now we have to go to a Markov decision process. So I had mentioned the previous lecture about Markov decision process. So a reinforcement learning algorithm. Reinforcement learning problem is modeled as a Markov decision process. So what is a Markov decision process? Any RL task which has state, action, and reward, if the state, action, and reward, if the dynamic satisfies the Markov property, then you can say it is a Markov decision process. So you have a decision, the decision is to choose the action. You have a reward based on which you choose the action. You also have a state on which the reward and the next state depends on. So the Markov property is satisfied for this process, for this process of the process. In the sense, what I mean is you have states, actions, and rewards. If this is satisfied, you say it is a MDP. If the state and action spaces are finite, it is called finite MDP. And in many, to at least show a lot of properties, you assume the finiteness. So a finite MDP is defined by state and action sets. So your state and action set will be finite, and you will have only one-step dynamics. You don't have to look at the entire history. So it makes showing properties of algorithms much easier than an infinite MDP. So this is the one-step dynamics which we had seen in the previous slide. So given any state and any action, any state S and any action A, the probability of the next state and the reward is given by the one-step dynamics. Okay, and we have seen that if the Markov property is satisfied, this is enough. You don't have to look at the entire history. So from just this dynamics or this model, whatever you call it, the translation probability, you can calculate all the quantities which are required to solve the problem, to write a reinforcement learning algorithm. So these two are summations. I'm writing it as summation. So I have the PPT has correcting, but anyway, I'm writing. I don't have to switch between the PDF and PPT. So I'm writing just summation symbol here. Now look at some quantities which can be derived from this. If you know this, you can derive many other quantities. This is the most fundamental thing, which is the one-step dynamics. Look at this expected reward. For a particular state and a particular action, what is the expected reward? Okay. So that is expectation of the reward you get at time t+1. So this is a probability. This is a probability, right? So you take expectation over the reward given st is equal to s and at equal to a. So the current state is yes, current action is a. What is the expected reward I'll get at that time? Next time t+1. Okay. So this you can find from this dynamics. You just say take the summation over all the s prime. And you multiply, there is an R here, so this is the expectation. You take expectation. Okay, so you first find the I think you call it marginal. So you sum over all this. S is a finite. We assume in this case to be finite set. So you take the summation over S prime of this. You will get a marginal. You multiply with R. and then again take summation over the set R. Then you will get the expected value of the reward at time t plus 1 given the state action at time t. Okay. This is termed as RSA. Okay. Why is it termed as RSA? Is this term does not depend on the time t. This does not depend on the time t. Okay. So look at this. On the left hand side, you have no dependence on the time. This is true for all t's. Okay. So this quantity does not have to depend on time t. So given a state S and action A, what is the expected reward? That is R of SA. This you can find from this dynamics. This is the first quantity which you can estimate from the probability, translation probabilities. The next is, this is R of SA, and the next is what is called as state translation probabilities. Okay, this is the state translation probability. Again, this is a summation. Okay, so you have what do you mean by state translation probability? I had mentioned this term yesterday also. What is the next state given the current state and current action? That is the state translation probability. That can also be computed from the dynamics, this equation. Only thing you have to do is sum over all the rewards. Then you will get P S prime given S and A. And there is one more quantity which is also quite useful in algorithms. It is called expected reward for state action next to state triple. Okay. So you have expected value of RT plus 1 given ST equal to S, AT equal to A, and ST plus 1 equal to S prime. So I will go to the PPT and show this equation, PDF and show this equation. Just a second. So if you have some questions, you can stop me, you can ask. So I've shared the PDF. Okay, so this is the same equation. So you have on the numerator, okay, you have summation, you multiply R into this quantity, which is the dynamics which we had seen. Okay, so this will give you the, so this will give you the expected reward at S prime, S and A. You divide it by the probability of S prime given S and A, you will get this. Okay, so this term on the numerator, denominator gives the state translation probability. What is the probability of translation to state S prime given S and A? And on the numerator, you have for S prime, what is the expected reward given S and A? At S prime, what is the expected reward given S and A? divided by the probability of S prime given S and A, you get the expected reward for the state action next to state triple. Okay. So this this term on the left-hand side is also used in many algorithms, and the example which we'll see today towards the end of this lecture also will have the expected rewards for the triple, not for just state and action. It will also be for the triple. Okay, so I'll go to the PPT again and continue. Okay. Okay, so again there is an equation. Okay. I think I'll go back again. So this equation is an important equation, so I have to go back. So let me go back to the PDF. Okay. So I'll use this PDF because I cannot be switching between both. So I will use this itself because from now on you will get some equations. Okay. So next is value functions. So this term also I had mentioned yesterday. So value function, if you recall, says how good a state is. Okay. There are two different value functions. One is state value function, one is action value function. Okay. In state value function, you say how good a particular state is. If you go to a state, what is the expected reward? In some ways you will get what is the best possible or what is the expected reward you can get if you follow some policy. Action state action reward is action value function is if you go to a particular state and take an action, what will be the rewards you will get if you follow a policy, some policy pi. So these value functions are functions of states, and they estimate how good it is for an agent to be in a given state or how good a particular state is. So this is defined in terms of future reward and which is expected. So it is not just the current immediate reward. You also consider all the future rewards. The value function considers the entire accumulation of rewards. We had seen about returns. We use that concept here in value functions. So recall that yesterday we had seen in the slides what is a policy. Policies in this notation, if you remember, I had explained that yesterday. So you have a policy pi which says that at a particular state, yes, what is the probability of choosing an action A? Okay. That is the policy pi. So this I had mentioned yesterday. You can check the slides yesterday, last slides, and you can see that. Now let's look at the value function. So this concept is, you can say, the first important thing in a reinforcement, MDP or a reinforcement learning problem. So a value, what is a value function? This is the value function on the right hand side. This is unique to MDPs and reinforcement learning. So value of a state under a policy pi is this V pi of S at a state S. Value of state S under a policy pi is V pi of S. How is it defined? This is the definition. Okay. We had seen the term GT before. Remember this? GT was, when I started the lecture today, I was mentioning about GT. Okay. There were two different tasks. One is episodic, another is non-episodic, and I had mentioned how to accumulate the rewards in both cases. And V pi is simply the expected value of GT given ST is equal to S. Okay, given the present state is S, what is the expected rewards you get in the future, accumulated rewards you get in the future, if you follow policy pi. This is important. So it will change with different policies. If I change the policy, I will get different value function for the same state. Okay, this depends on the policy you follow, and it also depends on the state you are at. This is the first unique concept for MTPs and reinforcement learning, and this is basic. So for any algorithm, you should know what is a value function. And today we'll see an algorithm and also code, which is called policy iteration, which improves on this policy by estimating this value function. So I'll go further. What does this expectation denote? E pi. What does this denote? Okay, this is expectation. Is the expected value of the random variable, that is GT I mentioned is a random variable because the rewards are random. It is the expected value of the random variable GT when the agent follows policy pi. Here T is the time step. T is any time step. So this T here, GT is time step. If you have Markov policies, Markov property, then you can show that this quantity is not dependent on the time T. See, here we have a dependence on T. Here there is no dependence on T. That the reason is for a Markov property, if the Markov property is satisfied, you can show that this will be same for all T's. Okay. For a particular S and a particular policy. Okay. If you fix a policy in a particular state, it will be fixed. It does not depend on time. You can show that if the Markov property is satisfied. I'll not go into that, but you can show that. If you have a terminal state, if it is an episodic task, you sometimes assume the value function of that particular terminal state is 0. This is for convenience. So if you have to, there are algorithms based on dynamic programming. So in those algorithms, you sort of do recursion. So here, if you assume that the value of the terminal state is 0, then it will be very useful. Okay. So we assume V pi of ST, the capital T, to be 0. That is the terminal state has value 0, value function, because there is nothing after that. It is the last state. Similarly, the value of taking an action A in state S under a policy pi is denoted by Q pi SA. So there is a difference between this term and the term which we had seen in the previous slide. So this is V pi S, right? It depends only on S and policy. This is action value function. This is called action value function. Q, the term Q, you may have heard of the algorithm Q learning. So that comes from this Q. This the Q notation is this. So this Q is the action value function. It is the value. It is the expected accumulated reward starting at state yes. Then you take action A, and then following policy pi. Okay. At some time step T, you take action A, you are at state S, and in the future you follow the policy pi. Okay, this is called action value function. So the expected return starting from yes, taking an action A, and after that following policy pi. Initially you take action A, but from the next step you follow policy pi. That is called as action value function. So this again is independent of T. So if you can show if the Markov property is satisfied, this Q pi SA will not depend on T. So you can say expected value of pi, expected value over pi. There is expectation over the policy. Pi can be a random policy. Remember, your policy can be stochastic. At a particular state, I can go to some action with some probability. And there is also an probability in this dynamics. So if you are at a state, some yes, an action A, you can get the next state and reward as a probability. So it is not deterministic. That is the one-step dynamics we had seen. So you can expand it again. This is the equation we had seen for GT. Okay. So this is again conditional probability that ST is equal to S and AT equal to A. Expected value, expectation taken over the policy, the randomness in the policy, and also the one-step dynamics. This is called, as I mentioned, it's called the action value function for the policy pi. Okay. If an agent follows a policy pi and it maintains an estimate or average for each of the state encountered of the actual returns that have followed the state. So this point is saying how will you estimate the B pi and Q pi? So how to find? We do not know the B pi and Q pi. How to estimate this? So how to estimate this? You each time you encounter a particular state. Okay. So if you encounter a state, you accumulate. So you add all the returns. So you have an average. So the returns that follow that state. So what are the returns that follow the state? You take an average of that. That will converge to the state's value B pi. So you keep track of the actual returns that have followed a particular state. And you in some way find an estimate of, we'll see there is an approach called as policy evaluation. In that method, we will see how to estimate V pi and Q pi. So we have to find V pi and Q pi. Okay. We'll see that. We'll see how to do it. So if we separate averages for each action taken in a state, then we can show that these averages will converge to the action values Q pi. Okay. So this again has to be more specific. So what do you mean by average? Average over what? So average of what values? So that is not very clear from that. That will we see in as an equation in some slides. It will be clear in some slides. So there is a method known as policy evaluation. There we will see how to find this V pi and Q, estimate this V pi and Q pi. Before going to estimating V pi and Q pi, there is another fundamental. First property we saw was Markov property. There is another property which is also important in reinforcement learning, that is called as the Bellman equation. Okay. This is a particular recursive relation which is satisfied in this MDP. Okay. Look at this. This is the Bellman equation. So from this we will get the algorithm. Why is this important? Because from the Bellman equation you can get the policy iteration algorithm, and that is what is our first algorithm which we'll use to solve this problem. Till now we have not seen any algorithm to solve the MDP. I'm just talking about what is reinforcement learning, what is MDP, but I've not mentioned any algorithm which will solve this problem. So the first simple algorithm is a policy iteration algorithm that depends on this Bellman equation. So this Bellman equation is a recursive equation. First, we have to look at this Bellman equation before going into the policy iteration. For any policy, how to get the Bellman equation? So for any policy phi and any state yes. Okay. Look at this set of equations. So this is the definition of the value function which I have shown in the previous slide. I'm expanding this GT. I'm using the definition of GT. This is the definition of GT. Then what do I do is I write T plus 1 separately, RT plus 1 separately, and from RT plus 2, everything else. Okay. I write RT plus 1 separately, and I have a gamma here. And again, from RT plus 2 separately. Then, look at this. This is an expectation over the pi. So I take the pi A given as the summation over all A. Okay. Then there is also one-step dynamics, right? So then I take the summation over the states and summation over all the rewards, the probability one-step dynamics. Okay. If you have some question, you can ask. So this is an important equation which you have to know. If there is something you want to ask, see, what I'm doing in this step is expanding this expectation. Okay, that's all I'm doing. So that's all is being done. So how do you expand this expectation? So you have expectation over pi. Okay, you have written the policy here. You have written the dynamics. There are two random quantities. One is the policy, it is stochastic, and one is the dynamics, that is also non-deterministic stochastic. So you have to take expectation of considering this and also this property. This is a probability, this is also a probability. Okay. So you have to consider expectations for both of them. So first over the policy and then over the dynamics. So this R will be the RT plus 1, this term. Okay, and again you will have expectation over pi. You take, so what I do is expectation of this quantity plus expectation. So expectation of sum is sum of expectations. Okay? So there is a property of expectation. So I use that property, expectation of RT plus 1 plus expectation of the second term. Okay, so that's what is given here. Okay, and what can you do here is the second term you can say is gamma times V pi of S prime. So this is the important part here. See, here you have V pi of S. If you follow this, then that's enough. So in the Bellman equation, you will have V pi of S prime. Okay. Okay, so this is the same thing. So this term is V pi of S prime. Okay, you can see, check it to be V pi of S prime. Okay. That is what is given here. And this equation, that S and S prime here, you have S on the left hand side, V pi of S, and you have S prime on the right hand side. This is called the Bellman equations. This is a Bellman equation for the value function. You also have a Bellman equation for the action value function. Okay. Very similar to this. Why is this important? The reason is we can show the value function V pi itself is the unique solution to this Bellman equation. So if there is a V pi, it has to satisfy this equation, right? So this V pi here, there is a V pi, and here also there is a V pi. And you have probabilities here and here. If you solve this Bellman equation for V pi, you have found the value function. That is the use of this Bellman equation. you can have a recursive algorithm based. There's one of the very old algorithms called dynamic programming. This is based on dynamic programming. We will not see that based on this Bellman equation. That is a recursive. So you start at the terminal and go back to the start state. In some ways, it's a recursive algorithm. So here, the actions A are taken from the set AS. This I had mentioned before. The next states are taken from the state S, and the rewards is taken from the set R. Okay. So this is, I think, already clear. So this is fine. So if you have some questions, you can raise. So this is important. This Bellman equation is important. And the value function is one which satisfies the Bellman equation. If you solve the Bellman equation, you will get the value function. And that is what we will see is being done in the algorithm today, what we are going to see, the policy iteration algorithm. So this is the equation for V pi. Okay. It expresses the relation between the value of a state and value of the successor states. Okay, so it's again the same slides. Okay, I have to go further. Okay. Okay. Now there is the next one. We have seen value function. What about? That's not enough. We need optimal value function. Okay. So look at this. So this V pi depends on pi. Okay. Depends on the policy. So what is the optimal policy? For a different policy, you will have a different value function. So how do you define an optimal policy? For that, you need a concept of optimal value function. So which is the best policy? So you have a different one policy, you have one value function. You have another policy, you have another value function. So which is the best policy? For that, you have to look at the concept of optimal value functions. So solving an RL task, so this is fundamental, means that you find a policy that achieves more reward over the long run. So it's the basic idea in reinforcement learning. We define an optimal policy in this way. What is an optimal policy? Okay. Which policy is better? Which policy is not better? Okay. How do you compare two policies? This is the way you define it. It is defined based on the value functions. Okay. A policy pi is considered better than policy pi prime. There are two policies pi and pi prime. One policy pi is better than another policy pi prime if the expected return is greater than or equal to, of pi is greater than or equal to pi prime for all the states. In short, as a symbolic notation, I write pi greater than or equal to pi prime. That is, pi is better than pi prime if and only if v pi of s is greater than or equal to v pi prime of s for all s. Okay. Now, you know that there is an optimal policy. That is, there is a policy which is better than everything else. That can be shown mathematically. That can be shown. We can show that there is one policy which is optimal. Okay, it is greater than everything else. Okay, that's what is given here. There is always at least one policy that is better than or equal to all other policies. This is the optimal policy. Okay. The proof is not given here. The proof, I think, we can go once. I think you can check some online sources there. You can show that there is always an optimal policy. That is, there is a policy which gives higher values at all the states compared to all other policies. That can be shown. There is an optimal policy. Okay. This policy is normally denoted by the asterisk pi star. So the value function of this policy is denoted as V asterisk, V star. Okay. So V star is maximum for all the policies, V pi of S. Okay. Okay. And since there is an optimal policy, pi, if say policy, some policy gives maximal for one state, okay, I'll say it like this. If there is an optimal policy, it will give maximal for all the states. Okay. Similar to state value V, you also have optimal action value function, Q star. We have seen Q pi. Similar to V pi, we have seen Q pi for a particular policy. We can also define Q star. That is the optimal action value function. The definition is the same. You maximize over all the policies pi, Q pi of S and A. That will give you the optimal action value function, Q star. Okay. This depends on both the state and the action, while the optimal value function depends only on the state. Okay. You can write Q star in terms of V star. Q star of S comma A is the reward, expected reward you get plus gamma times B star of ST plus 1. That is the value you get from time T plus 1. So this, see, Q star is what you get when you follow the optimal policy. Okay, first step I choose the action A, I get a reward, I go to a step T plus 1, ST plus 1, and from there I follow the policy pi star. That will be the Q star of S and A. Okay. So in this equation, they have related Q star and V star. Because V star is the value function for a policy, that is the optimal policy, it must satisfy the Bellman equation for that optimal policy. This is called the optimal Bellman equation. Okay. This is, or you call it Bellman optimality equation. If you write the Bellman equation holds for all V pi, all policies V pi. So all value functions V pi. So it will also hold for optimal policy V star. For V star, it is term, there's a special term, you call it Bellman optimality equation. Okay. Because it is the optimal value function, the consistency condition in V star can be written in a special form without reference to any policy, without reference to the optimal policy. We'll see that, and this is known as the Bellman optimality equation. So this Bellman, we'll see this Bellman optimality equation, and from that equation we will get the what is known as policy improvement algorithm, and from the way you estimate V pi and Q pi, we will get the policy evaluation algorithm. Together it is called the policy improvement. Okay. Policy iteration. So it is called policy iteration. Policy improvement and policy evaluation. So what does this Bellman optimality equation express? This expresses the fact that value of a state under the optimal policy must be equal to the expected return for the best action for that from that state. Okay, so look at this equation. Okay. So this, see, earlier we had related Q pi and V. So Q pi in terms of V star, Q star in terms of V star. Okay, this is writing Q star in terms of V star. We can also do the other way around, write V star in terms of Q star. This is writing V star in terms of Q pi star, or Q star and Q pi star are same. Okay. So you write V star in terms of Q star. Okay, to find the best action for this Q pi star, S and A, you will get V star of S. Now expand this Q pi star of S comma A. This is the definition of this. Again, you write what is GT. This is GT. Again, you write t plus 1 and the rest of the things separately. Okay. Then this will be V star. You can show this is V star. So, so this, I think this expectation is only for this, and you have V star here. So, okay. See, this expectation is over both the policy and the one-step dynamics, but this expectation is over only the one-step dynamics, not over the policy. So this is both over the policy and the one-step dynamics. Here I have only the dynamics, that is the next stated the reward. So here I have V star and I have this V, and I expand this using the probability, I get this equation. So look at this equation. So this is the max. Here you have a max term here, and here you have the, on the left hand side you have V star of S, and on right hand side you have V star of S prime. If you solve this equation, you will get the optimal value function. Okay. Thereby you can solve the problem. The only thing is we have to solve this equation. Okay. So this is optimal value function. Earlier, if you solve the Bellman equation for some policy, you will be able to determine the value function for that policy. But that is not the solving problem. Solving problem, you have to find the optimal policy. For that, if you solve this equation with just max here, you will get the optimal value function. So from that, you can get the optimal policy also. The last two equations are called as Bellman optimality equation, and they are crucial in any reinforcement learning algorithm. Similar to the Bellman optimality equation for V star, we can have a Bellman optimality equation for Q star. It is very similar. Okay. So you have expectation over RT plus 1. How you show it is very similar to the previous slide. Plus gamma times max of A prime. That is the next action. Q prime of ST A prime. Okay. This you can expand as this. This is the Bellman optimality equation for Q star. From this equation, you can directly also get the optimal policy. Okay. How do you find the optimal policy? It will be the action which maximizes Q star SA. That's all. That will be the optimal policy. Suppose at time step yes, I want to say what is the best action. Okay. I want to find the best action. I just find Q star. If I have Q star SA, I find the A which gives the maximum Q star SA for a particular yes. That will be the best action on that particular state. So if you know the optimal action value function, you can straight away get the optimal policy. You have solved the problem. Okay. So how do you solve this equation? This equation is what determines the policy iteration algorithm. There are two basic algorithms. One is called policy iteration and one is called value iteration. Okay. We'll see one of them. Value iteration is also simple, but it involves some concepts. We'll see the policy iteration algorithm, and we'll see the code also for the policy iteration algorithm on a simple MTP. It's a toy MTP which we ourselves set. It is not from any practical example. It is from a toy example. Okay. And we can show that for a finite MTP, if the action state sets are finite, the Bellman equation of Bellman optimality equation has solution independent of the points. And this Bellman optimality equation solution will determine the optimal policy. So this optimality equation is a system of equation. This is a system, so you can write this as an vector. So you can write it as a system of equations. If there are n states, there will be n equations in n unknown. So you can have a matrix and you can solve for the solution. You can find the solution of that. So we'll see. We'll not look at that, but we'll look at a different algorithm called as policy iteration for solving this Bellman optimality equation. So we'll stop here. We'll continue after. So there is a break. So I'll stop here. I will continue after 10 minutes. So we will start at 5:35. Okay, so we will again start. Okay, so we will continue with the Bellman optimality equation. Okay. Complete the policy iteration algorithm. So that is the goal. Goal is to look at policy iteration algorithm and to look at the implementation of the policy iteration algorithm. Okay. So this Bellman optimality equation for the action value function can be stated as, if there are n states, can be stated as an n system of n equations in n unknowns. So this, I think this n states, this will be the Bellman optimality equation for V star, not for Q star. And Q star you will have action and state both. So you will have more number of equations in more unknowns. You have unknowns both the state and action. So this is talking about V star of S. The Bellman equation is talking about V star of S, not Q star of SA. Now let's look at how to solve this Bellman optimality equation and derive the policy iteration algorithm. Okay. So first, for this, we assume the dynamics, that is P, S prime, and R given S and A. That is current state is S, current action is A. The next state is S prime, and the reward is R. This is the dynamics. We assume that this dynamics is known. This probabilities are known for all the S prime, R, S, and A. This need not be the case in real example, real applications. You may not know this. You may only know it from interaction. For that, you need model-free algorithms. So last class I had talked about model-based and model-free. So this assumes we have the model. It is model-based algorithm. Okay. If you have the knowledge of P, you can solve this equation for B star, and we can get the optimal value function. Once we have V star, how do you find the optimal policy? So for each state, there will be one action, one or there may be even more action at which the maximum is obtained in the Bellman optimality equation. Look at this equation which we had seen before. Okay, this equation. So if you know V star, okay, you can find Q star. V star is defined in terms of Q star. If you know the dynamics and V star, you can find Q star. And from Q star, you can find the optimal policy by finding the one which action which gives the maximum Q star for a particular state. But this is not what we are going to do. This is if the probability, the dynamics, the one-step dynamics are known. Okay. So from V star, you can get Q star. Okay. And any policy that assigns non-zero probability to all these optimal action is an optimal policy. Okay. So if you have the Q star, you can simply find the action which maximizes this. That's what I just now mentioned, to find the optimal policy. From V star, you go to Q star, and from Q star, you go to Y star. This is straightforward. There is not different. First, you solve the n equations in n unknowns for V star, and from V star, you find the Q star from the previous equation, which I just now shown. And from that, you get the pi star. And our goal is to find pi star, the optimal policy. Okay. Finally, that is the goal. Hence, at the cost of representing a function of state action pair, can if you have some question, you can ask. Yes. Is there some question? We have not yet seen the algorithm. This is just an idea. This is not the algorithm. So this is, if If you know the dynamics, you can solve the equation using standard numerical techniques, numerical methods. So if you have a system of n equations and n unknowns, you can solve it using iteration. You can have Gauss-Seidel method. There are standard methods for that. This is not what we are seeing. What we are going to see is something different. We'll see that, and we'll see that just now. So the what there's a claim here is at the cost of representing a function of the state action pair, instead of just the states, the optimal action value function allows optimal action to be selected without having us to know anything about successor states and their values. So you don't have to have Q star of S comma A. You can find Q star of S comma A from V star of S. Okay. So this is if the dynamics is known, you can solve for V star and go to Q star and get pi star. Okay, now let's go to the algorithm. That is the basic goal of this lecture. There are two steps. The algorithm is called policy iteration algorithm. There are two steps to this algorithm. One is called policy evaluation and one is called policy improvement. So the idea of these two are done alternatively. First you do policy evaluation, then you improve the policy. Again you do policy evaluation and improve the policy. You keep on doing both of them alternatively till you reach the optimal policy. This is the policy iteration algorithm. You iterate between evaluation and improvement. Okay. This will give you the optimal policy. Finally, you will converge to the optimal policy. You can show that. There are two different components here, policy evaluation and policy improvement, and you alternatively do both till you find the optimal policy. First, we look at the first component, policy evaluation. This is true for any policy pi, not just the optimal policy. This is true for any policy. How to evaluate the value function of that policy. So we are not given V pi, we are not given Q pi. We have to estimate V pi, we have to estimate Q pi. Okay, how will you do that? For the banded problem, we had seen that in the previous lecture. We will see this for the reinforcement learning problem. There we saw for Qt of A. Here we are seeing for V pi and Q pi. Okay, so this is called in dynamic programming literature, it is called policy evaluation or it is the prediction problem. So the other term used is critic. So you call this the critic component and the other to be the actor component. You may have heard of the term actor critic. So the critic in some way does the evaluation, the actor does the improvement. Okay. If you look at it that way, this is the precursor to an actor critic algorithm. Look at this equation. This we had already seen before. The definition of V pi. This is the definition of V pi. So is the expected value. So I think there is a term missing here. So it is given St is equal to S. So that is missing here. So here St should be, there is a conditioning here that is missing. So conditioning St is equal to S. So RT plus 1 plus RT plus 2 gamma times RT plus 2 and so on, given St is equal to S. Okay. This you can write as RT plus 1 plus V pi of St plus 1. Okay. You can write the remaining as V pi of St plus 1. And this pi, you can expand the expectation like this and you can get this equation. This is the Bellman equation for this is the Bellman equation which we saw for your policy pi value function policy pi. This is the first thing which we saw. I'll go back to that and show that. So this is the first Bellman equation we saw. We had seen 4 Bellman equations. What is the Bellman equation for V pi, Q pi, V star and Q star? Okay. So this is the Bellman equation for V pi. This is this one. This one. V pi and the first Bellman equation, V pi here. This is the equation which we have recalled in the current slide. Okay, this is the same thing. V pi here and V pi star here. V pi S star here, S prime here. Okay. This we had already seen. This is just recall that this pi is the policy. It is the probability of taking action A in the status under the policy. This is the policy pi. Okay. Now, how to do the evaluation? So, with this, how will you evaluate the policy? How will you find this V pi? Okay. You have to find V pi. If you know this, you can solve the system of equation. But if you don't know this, what will you do? So the expectations are subscript. Okay, this is another point which is to note. The expectations are subscripted by pi to indicate that the conditioning is on the random policy. The policy has some randomness, so the expectation is on that randomness. Okay. The existence and uniqueness of this V pi. So if you solve this, will you get a solution? Yes, there will be a solution. There will be a unique solution. It can be guaranteed as long as you have an terminal state or you have gamma less than 1. So you have eventual guaranteed termination from all states, or you say gamma is less than 1. If either condition is satisfied, then V pi is guaranteed to exist and it will be unique. So there will not be just 2 different V pi satisfying the same Bellman equation. This will also be unique. So this point I had already mentioned in the previous slide. If the one-step dynamics are completely known, then you just have a system of linear equation. You can solve using numerical methods to solve the n system of linear equations in n unknowns. Okay. There are, we will, for our purposes, we will look at some iterative solution methods which are suitable for this finding the V pi. Okay, estimating the value function of a policy. So here our goal is to estimate the evaluate of a policy, how good a policy is at a particular state, at any particular state. Okay, so the idea is this: you select some value function V0, V1. So you consider value functions which are arbitrary. It need not be for any particular policy. V0, V1, so on. These are mapping from these are you can think of this as, you can call this value function, but what they are really is they are mapping from the state space to the real numbers. So it will give value for each of them, each and every state. So you can these are done found iteratively. First you choose V not arbitrarily. So for each state you will have an arbitrary number. Then you iterate using an iteration rule which you will see, and we will get V1. And from V1 we will get V2. Iterate using the same update rule, we will get V2. What can be shown is V1, V2 will, if you follow this rule, V1, V2, this Vi will converge to V pi. Okay. And this is what is the policy evaluation technique which we will use. Okay. You start with an arbitrary V naught, that is a mapping a function from the state space to the numbers, real numbers. Okay. And you do the update rule like this. This is the update rule. Okay. This rule comes from simply from the Bellman equation. It is same as the Bellman equation. Here you had pi. Here also you had pi. So you use V k here. You do this, you get Vk plus 1. Okay. and you plug in vk plus 1, you will get vk plus 2. V naught is arbitrary. You can fix any function. Okay. You get V1, and from V2 you get V3, and so on. Eventually, you can show that this Vk will go to V pi. The reason is you have pi here. Okay. Note that you have pi here. Okay. And this dynamics is also given. Okay. You assume this is also known. Otherwise, you cannot find this quantity. Why is this the case? The reason is there is something called fixed point. In mathematics, there is a concept called fixed point. So if you substitute V pi here, then V pi here, then you will get V pi here. See, if you have V pi for Vk, you will Vk plus 1 will also be V pi. That is, if that is the case, it is called a fixed point. Okay, and the Bellman equation has fixed point to be V pi. So we can say that Vk equal to V pi is fixed point for this update rule, because the Bellman equation for V pi, which we had seen the first Bellman equation, actually satisfies the equality. So we can show that with this update rule, the sequence V pi Vk converges to V pi under the same conditions that guarantee the existence of the fixed point V pi. Okay. This can be shown. It's not a difficult proof. It can be shown mathematically that Vk will converge to V pi. So what we have to do is just this: start with the V naught. Okay. Do this update, get V1. Do the same update, get V2, and go on. Finally, you will get converge to V pi. This is the policy evaluation. Okay. So this is called iterative policy evaluation. Okay. So you produce these Vks as successive approximation to the V pi's. So Vk will be an approximation, Vk plus 1 will be a better approximation, and so on. And eventually you will actually, if there are only finite states and finite action, you can show that you will go to V pi infinite time. So you apply the same iterative policy evaluation, the same operation to each state. So look at this. See, there is a dependence on S here. So you have to find Vk plus 1 of S for all the states S. Right? So you have to be, you have S here, and you have S here. And you have summation over S prime and R. You have to find this Vk plus 1 of S for all the S, all the states S. And from that, you will have to find Vk plus 2 of S for all the S using the same update. Okay. So you replace the old value, the Vk of S, with the new value Vk plus 1 of, with the new value obtained from the old value of the successor state, that is Vk of S. You get the new value Vk plus 1 of Vk of S prime, you get the new value Vk of S. You also need to know the immediate reward. So this is the immediate reward. So this one, this quantity. So this is, you take the summation over all the immediate rewards. Okay. So this is probability. This probability is also known, assumed to be known. So for this, you need to know the one-step transition probabilities and the policy also. You should know the pi of A given S. Okay. So this kind of operation, which is this update, is known as full backup operation. This in the book by Sutton and Bartos. This is called full backup operation because they are based on all possible next states rather than on a sample next state. So that's why they are called full backup operations. This is different terminology which is used in the book. So this is about the policy evaluation component. Okay. Next is the other component, which is the policy improvement component. Together, if you alternate between these two, you will get the policy iteration algorithm. So the idea is this: you start with a policy, some random policy pi. Okay. You evaluate the policy using the policy evaluation we had seen just now. And then you improve the policy to pi 1. And then again you evaluate pi 1, find b pi 1. And then again improve the policy and get pi 2 and evaluate pi 2 and so on. You keep on going till you find the optimal policy. We have seen the policy evaluation step. Okay. Now we will see the other component, which is the policy improvement step. Suppose I have a policy pi. How will I improve it to a better policy? How will I find a better policy? If there is a better policy, how can I find the better policy? This is not about evaluation. You are assume the value function b pi and q pi, action value function are known. I want to find a better policy. Can I find a better policy than pi? If such a policy exists, that is the policy improvement. In these algorithms are all model based algorithms, what we are saying now, policy iteration algorithm. There are other algorithms which are model free, like actor critic and Q learning. They also have, actor critic also has these two components. One is the evaluation of the policy by the critic and improvement of the policy by the actor. So this again is the recap of the same thing. So I'll go further and okay. Now we look at the policy improvement part, the second component of the policy iteration algorithm. Now you assume that we have determined the value function d pi for some arbitrary deterministic policy pi. So for simplicity, it can also be a stochastic policy, but you assume for simplicity it is a deterministic policy. You perform the d pi. Okay. Now we would like to know if there is a better policy. If there is a better policy, how to find that better policy? Or in other words, we would like to know, is it better or worse to change the new policy? So is it to the new policy? If current policy is the best, or is it possible to find a better policy? The idea is very simple and it is based on the same Bellman equation. Both evaluation and improvement both are in some ways related to the Bellman equation, optimality and Bellman equation. So if you remember the Bellman equation, you can get both these two algorithms, and you can also find go to the other algorithm, value iteration, and also dynamic programming. All the basic algorithms are straight away derived from the Bellman equations. There are 4 Bellman equations. If you know all the 4, then you can derive most of the basic algorithms in reinforcement learning. Look at this. We select some action A. So this is about Q pi. So we select an action, the action value function. We select an action A in the current state yes, and thereafter follow policy pi. The first action is A, and from the second action it is determined by the policy pi. That is how the Q pi was defined. If you recall, first action is A, AT is A, and from the next action it will be pi. It will be determined by the policy pi. Okay, this is the we had seen before. Okay, this equation we had seen before. So if you expand, you can get this. So I had got this equation before. So you can write V pi into V star in terms of Q star and Q star in terms of V star. So this is not this. This one, okay. I can write Q star in terms of V star. Okay. So this was, I think, in one of the previous slides. So you had both ways. You can write Q star in terms of V star, and you can also write V star in terms of Q star. So that was given. The other direction was given, I think, by maximizing. So you find V star from Q star by maximizing the action. So that I think, yes, here. Okay, it's given. V star in terms of Q star. Okay. So this, what we are saying now is the first way of writing. You write the Q pi in terms of V pi. So that was for the optimal equation. You can also write it for any policy. So this we had not seen. So earlier we had seen star here and star here, asterisks here and asterisks here. Okay. You can also write Q pi from V pi from, you can also get Q pi from V pi. Okay. So the idea is the same. You expand you write the definition, you write it as two terms, first reward and then next rewards. Okay. You can show that the next rewards will be, if you sum them, that will be V pi from the next state. Okay. So this is also true for any policy. It is not only true for the optimal value function and action value function. The idea of seeing that is same as the Q star and V star. Okay. The idea is the same. So now how to improve? So our goal is to improve the policy. Okay. Suppose I have some policy. Is it possible to get a better policy? So how do you check that? So you have to check this. If you have two policies, if one thing which we know is if a policy is better, its value function will be greater than the. So if you remember, which is a better policy, there was a definition for optimal policy in one of the previous slides. I had written pi greater than pi prime or pi prime greater than pi. If V pi of S is greater than or equal to V pi of S for all states. Right. So this was the definition of what is better. So it was there in one of the previous slides. Okay. So you can go back and see that. You can see that. So I think it was one of the earlier slides. So this one, right? Which is a better policy? Okay. How do you define better policy? Is based on this right hand side equation. If the V pi's are greater. So remember this. Okay. Now we will see how to find this better policy. We know V pi. We want to find if there exists a V pi. There is a pi prime which is better than that. That has a V pi prime which is greater than V pi for all states. See, you can get a policy from this also. Right? You can get a policy. The idea is this. From Q pi, you can get another policy which maximizes the Q pi's. Okay. See, what I'm trying to say is I fix a pi. Okay. I find a A which maximizes Q pi SA. I say that that is the policy pi prime, pi 1. So if this is pi naught, that will be pi 1. That maximizes. See, I will have V pi. So this I will have pi naught. Let me start with some arbitrary policy pi naught. Okay. Then I will find V pi naught. I will evaluate the policy and find V pi naught using this iteration. Okay. I will find V pi naught, and from that I will find Q pi naught. From Q pi naught, if I find an action that maximizes Q pi naught S of A, the action which maximizes Q pi naught S of A for S, and say that that action is the action I take at state S. I call that policy pi 1. Okay. I can show that the V pi you get from that policy pi 1 will be greater than V pi naught. If that can be shown, we can conclude that phi1 is better than phi0. The way you find the better policy is maximizing and finding the action for this particular state. Okay. So we see that as an equation. Okay. So that is what is given here. So the key criterion here is whether this is greater than or less than v phi. So this one is whether it is greater than or less than v phi of s. So it may be greater for some action, it may not be greater for another action. If it is greater, suppose you say that v pi q pi of s comma a is greater than v pi of s. For some action, q pi of s a is greater than v pi of s. That is, if it is better to select an action a once in s and then follow policy pi, then it would be better to follow. Then it would be better than it would be to follow policy pi all time. Then what we can expect is every time you see the state yes, you select a instead of the policy pi. And we can show that this thing, that is following a every time yes occurs, is better than following pi. Okay. This can be shown. This can be shown in general. This is true, and this can be, and this is the key concept which is used in policy improvement. So by maximizing q pi SA, you can find a better policy. That is the basic idea, which is again mentioned here. Okay, so suppose you have, so this is again written as in equation. Okay. Consider deterministic policies for simplicity, though this can also be generalized for stochastic. Consider phi and phi prime to be two deterministic policies, okay, such that for all states, you have this q phi prime s is greater than v phi s. That is, if I select an action based on policy phi prime first and then follow policy phi, that is better than following policy pi. And I'll again repeat it. Suppose you follow policy pi at the first step and then follow policy pi, that is better than following policy pi always. Then you can say following policy pi prime always is better, or pi prime is a better policy than pi. Okay. If this holds, then we conclude that pi prime, since it is greater than or equal to, if it is strictly greater, it will be strictly better. If it is greater than or equal to, it must be as good or better than pi. Okay. This is the concept which is used in policy improvement step. Okay. How do you do this? How do you do this is straightforward. Okay. So that's given in few slides later. So why is this the case? Because if you find v pi, if this holds, the argument is v pi prime of s will be greater than or equal to v pi of s. Okay. This can be actually shown. This can be shown. So if this is the case, then pi prime is better than pi, or better than or equal to pi. Okay. So if there is a strict inequality for this first equation, this equation, then there will be a strict inequality for at least one state in the second equation also. Okay. This can also be shown. In that case, it will be strictly better. Pi prime will be strictly better than pi. Okay, so this is the idea used to improve the policy. So the step is one step. It's just maximize q pi over all the actions. So that is also written in, I think, some next, I think the next or next slide. So one more observation here is the two policies are not same. Okay, pi and pi prime are not same because see, if you have maximal see if what is given here is, okay, what is given here is, suppose you have a deterministic policy phi and you have another change policy. I have one deterministic policy and some other policy phi prime which is different from phi at only one state. Everywhere else it is same. At only one state it is different. That is the state, yes, they are both different. So this is A and this is not A. So we have two policies. One is phi, one is phi prime. They are same except at yes. Every other state they are same. At yes state yes they are different. Phi prime will give A and phi will give something else, some other action. Okay. If you see that phi q phi s A is greater than b phi s, that is choosing A, that is phi prime of s, is better than, strictly better than b phi of s, the value function for the policy phi at s, then the policy phi prime is better than the policy phi. So we can show this. We can show why is this the case. Look at this, the reason for this. Okay, the reason is not difficult to see. Why is this the case? Okay, so what we have is b phi is less than q phi of, this is what we have. So the current policy value function for the current policy is less than or equal to, if you follow the policy phi prime at the first step and phi later on. And what we want to show is, if this is the case, then b phi prime of s is also greater than or equal to b phi of s. If this is the case, then phi prime is a better policy than phi. How to show that is just by expanding the term. So the term on the left hand side, right hand side. So if you first write the equation for q phi, so this was given before. Okay. This was given before. Again, you expand it, you will get look at this. So this has another concept. See, v pi, you have v pi here, you have q pi here. This is true for all states. So this is also true for state st plus 1. So you will have a inequality here also. I am having v pi and q pi here, right? So this v pi is less than q pi for all states, not just for s. It's also true for st plus 1. So I write q pi again, and I again expand it for separating rt plus 2 and st, b pi of st plus 2. And I keep on doing this. I keep on doing this. I will get only rt plus 1 gamma times rt plus 2 dot dot dot. You go on till, if there is a terminal state, till you get for the reward of the terminal state, and that is exactly v pi prime of s, and that will be greater than v pi of s. Okay, so this is the argument which is used to show, if you follow a policy at one step and follow some other policy at another step that is better than following the other policy always, then the policy you followed at the first step is better than what you followed the second policy, what you followed afterwards. Now, how to do the improvement? Improvement, you just maximize, find the maximum. That's all. So this is the way in which you find. So this is one-step procedure. You do the policy improvement. So how do? You maximize. Why is this the case? This will be giving. So this will give you a q pi, which is. So what will this give? So this will give a q pi of SA, which will be strictly greater than. So you will have q pi prime SA will be strictly greater than q pi SA. So v pi SA. So that will mean that pi prime will be a better policy than pi. So it is natural extension to consider changes at all states and at all possible actions, and you select at each state the action that is best according to Q pi SA. Okay. You find the one which maximizes this for all actions, and you consider that to be the policy pi prime. For all actions you do, for all states you do that. Okay. This is just expanding this Q pi and you just get this. Okay. So you don't have to write in terms of Q pi, I have V pi. So what do I have? I have a policy pi. Earlier we saw how to find V pi. Okay. Recall that. So I'll go back. So you find V pi using the policy evaluation, right? This will converge to V pi. Okay. Take that V pi. You have some start with some policy pi naught. Using this, you find V pi naught. Take that V pi naught, plug in here. Okay. Plug in here. You will get pi 1. Okay. And you find V pi 1, plug it in here, you get pi 2. You keep on doing it, you will find the optimal policy. So this is the basic algorithm for policy iteration. So the greedy policy takes the action that looks best in the short term. That is, this maximization is in some way greedy. So if you just look at the maximum for the immediate, but that is based on Q pi, not on the rewards. Okay. So by construction, the greedy policy meets the condition of policy improvement theorem. So this policy meets the condition of policy improvement theorem. This is the policy improvement theorem. So this one. Okay. So it will be a better policy. So the policy improvement theorem is, I think, given not as a theorem, but yeah, you can also say this is the policy. This is same as the. So that was an argument why that is the correct. That is why prime is better. So this is the policy improvement theorem. So if Q pi of S comma pi prime is better than V pi of S, then pi prime is a better policy than pi. So this will be true for greedy policy. If you take greedy actions at using Q pi, so that will be a better policy than pi. So that is the conclusion. So yes, so the greedy policy, this is the greedy policy, will satisfy the assumption of the policy improvement theorem. So it will be a better policy than pi, than the original policy pi. Okay. This process of finding new policy from the original policy by doing greedy choices based on the Q pi, the action value function for the original policy, is called policy improvement. This is the policy improvement part. So we have two parts, policy evaluation and the policy improvement. You start with arbitrary policy, do the evaluation, improve that, again evaluate that, again improve that, keep on doing that. You will eventually go to the optimal policy. That is the policy iteration algorithm. Okay. How do you show that this converges? Suppose this new greedy policy pi prime is not better, but it is as good as the pi policy. So it is not better, but it is just as good as it. That is, the new greedy policy is same as pi. There is no improvement. If that happens, then you can argue that this pi prime and pi, which are both the same policy, is indeed the optimal policy. Because if you have this, right? So if you have, so this is, I think, so pi and pi prime are the same policy. So either you have pi or pi prime, it does not matter. So, pi and pi prime are both giving the same V pi's. So you have V pi prime and V pi prime on both the sides, right? If this is the case, you have max here. Remember, you have max here, okay? And you have some policy pi prime for which this holds, okay? Recall that this is the Bellman optimality equation. So this is indeed the Bellman optimality equation. If you have such some function V star, right? then that some function, let's call it v prime or v cap. That v cap is the v star. That is the optimal value function. So so this is C. This is the Bellman optimality equation, right? See, I'll go back to the Bellman optimality. We had seen 4 equations. I think this is the 3rd equation. So we had seen the Bellman optimality equation for V pi, right? So there you have the max term. Just looking for the Bellman optimality equation for V pi, V star. Look at this. This is the Bellman optimality equation. You have V star here, and you have max and V star on the right hand side. This is exactly what we have now. We have just, instead of V star, it is mentioned as V pi S. That's all, V pi. That's all, V pi prime. Okay. This equation and this equation are the same. What I had shown for Bellman optimality V star, and this is same. So we can show V pi prime is indeed V star. That is pi prime and pi both are optimal policy. So why is this important? Because I'm keeping on evaluating and improving the policy. What will happen eventually? So eventually you will go converge to the optimal policy. You will not, so at some point of time I will not be able to improve the policy. I will get the best policy. So that policy will satisfy the Bellman optimality equation. That's what is mentioned here. So eventually you will go to the converge to the optimal policy. So this equation is same as the Bellman optimality equation. Therefore, V pi prime must be same as V star, and both pi and pi prime must be the optimal policies. Thus, the policy improvement will give a strictly better policy, except the case when the optimal policy, original policy is already optimal. If you have optimal, then you will get optimal only. But if you don't have optimal, you will get a better policy. Okay. This is the claim in policy improvement theorem, the policy improvement part. So this is the claim we have for the policy improvement part. So what we can say is we will eventually converge to the optimal. So we have considered only deterministic policies, right? We can also extend this for stochastic policies, and the ideas also extend for that. So for policy improvement theorem also works for stochastic policies. We just have to use the definition for stochastic policy. So we normally in real examples you will have only stochastic policies. Okay. So you have to change the definition. So for stochastic policy, you have to write this. And policy improvement theorem will also hold for stochastic policy. You can show that the policy improvement theorem, that is if q pi of S pi prime is greater than or equal to V pi, then pi prime is a better policy, also holds for stochastic policies. That you can see using this definition of this expansion for a stochastic policy. So there may be ties. There may be 2 actions which may be equally good. In that case, you can break the ties arbitrarily. Okay. If there are several actions at which the same maximum is achieved, so all of them will be optimal. Okay. Instead of maximizing one action, you can also give probabilities to all actions which are optimal. So you can give some probability to all actions which are maximal. Okay. So instead of maximizing action, we instead each maximization. So there may be more than one maximizing action. All of them may be given some probability. Even that will be an optimal policy. So just a symbolic representation of the policy iteration algorithm. So we have seen policy evaluation, and policy improvement, both. Okay, so we'll combine both and we'll get the policy iteration algorithm. Okay, this is not the algorithm. This is the idea. The algorithm as in figure is there in the book, so I have not put it in the slides, but it is there. You can see that. But the idea is this. So before the actual how it proceeds, first if you have a policy, you improve it to get a better policy. Then you again evaluate it, get a better policy, and go on. So you start at pi naught. Okay. Some policy pi naught, any policy. You can say it is the same action for all the states. It does not matter. Okay. It can be any policy. You evaluate the policy. We had seen how to do this. Then you improve the policy. Okay. Get pi 1. Then again evaluate pi 1. And so on. We can show we will always, since in policy improvement, we will always get better policy. And when you go to the optimal policy, you will no longer be able to improve. So that will be the pi star, and you will get also B star. And this is what we have to get. So this is the goal of the reinforcement learning. We have to find pi star. That is what we have found. So this is the idea of this is the policy iteration algorithm. There is another very related algorithm called value iteration algorithm. Okay. That is also very similar, but it uses some more concepts. So I have not introduced the value iteration algorithm. Okay. So some more points. So each policy, pi 1, pi 2, is guaranteed to be a strict improvement over the previous one. It cannot happen that you will get two policies which are same but not optimal. If you are not able to improve, that is the optimal. Otherwise, you will be able to improve every time. There will be no case like you will not be able to improve for some time and then you will be able to improve. That will not happen. Okay. For a finite MTP case, okay, there are only finite number of policies. Okay. So you have finite states, finite actions. You can say there are only finite number of deterministic policies. Okay. So you will converge to an optimal policy and optimal function in finite number of iterations. Because at each step you are strictly improving, at finite iteration you will indeed converge to the optimal policy. This is for finite MTP. Okay. For an infinite MTP, you may converge eventually. Okay. This way of finding the optimal policy is called policy iteration. Okay. And in a policy iteration, policy evaluation step itself is an iterative computation step, starting with the value function for the previous policy. See, look at this step. This is an important step. So don't think this is one step. This is not one step. This will have many steps. Okay, finding V pi naught itself is an iterative process. This is not an iterative process, but this is an iterative process. So I'll show that again. You have Vk plus 1 and Vk, and we showed that Vk plus 1 will converge to V pi. Okay, that was an iterative process that will eventually happen, right? This is not one step. A policy evaluation is not one step. You can keep on doing the operation many number of times so that you converge to the P pi. Okay. So evaluation step is an iterative steps. You have to do it many times. If it is finite state, will converge in finite time, but otherwise you may not. So this improvement is not an iterative process. So this improvement, where is that? So this is the improvement step, right? This is not an iterative process. This is a one-step process, but evaluation is an iterative process. Okay. It's an iterative computation starting from the value function for the previous policy. This is no means the only algorithm for finding optimal policy. There are so many algorithms. There are many algorithms to find the optimal policy. Okay. This is one of the algorithms to find the optimal policy. Okay, now let's go to the implementation. So I have also a code which has implemented this policy iteration algorithm for a simple example. there is a code in Python. I'll show that, and with that we'll see that we'll then stop. So I'll just come in a minute. Just wait. Okay, I'll share the Python code. So this is available online. So this is a very simple example. There is nothing complicated with this. I just want to show some code. And there was also this asked in the previous lecture that the code, some implementation is shown. Yes. Okay, so this is the code for policy iteration algorithm. A Python, simple, very simple algorithm code. It's nothing complicated with this. So first, it's mentioning the procedure. So what is the procedure? This is just saying you have. So we had already seen this. There are state, actions, probability. This is the probability transition which we had seen, and this is the reward function for the triple, not for the couple. SA, it is for the triple. Okay. SA and the next state S prime. So the output is the optimal policy. So you start with an arbitrary policy, and you do the policy evaluation and policy iteration step both. So so I have the queues. See, okay. So I have B pi. So B of S. So this is the V pi. So this is the evaluation step. Okay, this is the evaluation step, and here they are using. I think they are solving it using some numerical techniques. What we had seen was an iterative computation. This step is the policy evaluation step, and then you do the policy improvement step. You find QSA which maximizes this. Okay, and this is what it does. So you find the one which maximizes the A, which maximizes this the quantity on the right hand side. So that is what is given here. So you have both the policy evaluation here and policy iteration. You keep on doing it till there is no change in the policy. Let's see that. I have this is a very simple MTP. So you have 5 states and 2 actions. Okay, I have 5 states. They have assumed it. So it is nothing. It is not coming from an real world application. It is just a toy example which has been created. So there are 5 states 0, 1, 2, 3, 4, and there are 2 actions 0 and 1. Either you choose action 0 or choose action 1. Okay. I initialize the state transition probability. So 0, 0, 1. So this is 1. So at state 0, if you take action 0, sorry, if you take action 0, you go to state 1 with probability 1.0. Okay. Similarly, you have for all the states. So 0, 1 is it's not given. Okay. So this is only for the states and actions which are given in this list. So 0 is, I think, the state, and 0, the second 0 is the action, and 1 is the next state. So that is what they have mentioned here. So no. So this is the current state, this is the action, and this is the next state. Okay. And for the rest, so look at this. They have initialized everything else to 0. Only these 5 values are 1. The rest of the array is 0. Okay. Only these 5 values are 1. The rest, everything else is 0. Okay. So if you have so if I have action 0 and state 0, then I will not be able to transition to. Okay. So what probably they have assumed is at state 1 there is only one action, and okay. So this is, I think, 1, 2, 3, 4 is the state. So the last is the state, and first is the state. Second is the action. Second value is the action. So at state 0, you can only take action 0. At state 1, it's probably like you can take action 1. At state 2, you can only take action 0. At state 3, you can take only action 1, and 4, you can take the action 0. Because there is no other choice which is given. So this is what is there. Okay, whatever is there, so this is what is there. And similarly, they have the rewards for the same combinations. Okay. Then they have set the gamma. This is the discount factor. Okay. And this is the value b pi of b pi. So it is depending on the states. So initially you start with the policy, some policy. So this policy is 0 for all the states. So the action is 0 for all the states. Okay. Then you do both the algorithms. You do, this is the outer loop. This is the policy evaluation, and this is the policy improvement. First for loop is the policy evaluation, and second for loop is the policy improvement. You find the best action, not greedy action. You find the greedy action here. Okay. Then you finally write till there is no change. You keep on doing both policy iteration and policy evaluation and policy improvement. Alternatively, you keep doing both till there is no change. If there is no change, in the policy, you stop and you print the final policy. Let's execute this. So the execution, I have executed this also. So let's see that. So I've already executed it. Let's execute it again. So this is what we get. So okay, I have to share the screen. Let me share the screen. Okay, so this is what I have executed and I have obtained. Okay, so if you have some question, you can ask. So there are, I think, 125 iterations. So in 125 iterations, it converges to the optimal policy. Look at the iteration optimal start. I'm starting with 0, 0, 0, 0, 0, all zeros, and finally I'm converging to this policy. 0, 1, 0, 1, 0. This is the final policy. There is no other change. Okay, and this is the value function for this policy. Okay, this is what we had. So if you go back, you can see that actually it's very simple to see that this is indeed the optimal policy. 0, 1, 0, 1. Okay. Look at this 0, 1. So you have 0. So only this the translation is the rewards are positive. The rest all actions the rewards is 0. So 0, 1, 0, 1, 0. So this is indeed the positive rewards, and you have converged to that's exactly the same 0, 1, 0, 1, 0. Okay. This is the optimal policy. You can change this code and tweak it. I can have something different. So let's see that also. So this is what I found online. So let's tweak it and see if this is also working for some other value. Okay. Suppose I have something else also. So I say P0, 1. Okay. I say again 1. This I say is 1.0. What I'm saying is at state 0, earlier there was only transition, only one action was available. Now I have two actions. Both the actions will, so if I take action 1 at state 0, I will go to action state 1 with probability 1.0. Similarly, I'll add the reward also for that. I'll add an higher reward. Okay. Let me add a higher reward. Okay. Let's say I'll add reward 2. I'll now save this and run this code. Look at this. So this gives a different policy. Okay. In this case, so the final policy is 1, 1, 0, 1, 0. So the first earlier this was 0. Now this is 1. The reason is 1 is giving better reward than 0. So we are getting 1 here instead of 0. Earlier, if you remember, we got 0 here. But here we have 1 here, which is giving higher reward, but the same translation. So this is better than 0. So I'm getting 1 here. So I think this is correct. This code is working fine. Okay. This is simple. I'm not claiming this is a state-of-the-art algorithm. This is a very simple algorithm, okay, which illustrates the basic policy improvement algorithm in reinforcement learning. So you can use Python. Python is quite simple to code, but sometimes if you have a large action and state space, you will have the code to be slow. It will take long time to execute. Okay. That's a problem, but that's how it is. So you can have this MTP has only 5 states. You can have MTP with much larger states. You can also have MTP which comes from a real example. This is our own example. You can have MTPs which comes from a real problem. And you can use the same policy improvement algorithm. Okay. So I have to stop here. So I have just I've illustrated the policy iteration algorithm. I have shown the implementation of that. We have started from a quick recap. So we have started from reinforcement learning. We had seen multi-arm bandits. We had seen MTPs, Markov property, Bellman equation. Finally, we had seen policy iteration algorithm and an implementation of the same algorithm. Okay, if you have some questions or some comments, you can say.
Hello, sir.
Yes, yes.
Sir, can you tell us how we can look at its scope towards research?
Research. Okay. See, research. This is very basic. So I have not gone anywhere close to research. So this, if you look at the book is available. This will be first 2 or 3 chapters. I think third chapter or 2 or 3 chapters in the book. The research here there are two ways in which you can look at it. One is applications of RL. Okay, if you want to apply RL for some problem, okay, that is what is more easier. So if you are going to apply this for some problem in, say, information retrieval, or if you want to apply it in some problem in wireless network, right, that is more easier. But if you want to do research in RL itself, that will need much more work. But if you want to apply it in some other area, say information retrieval, what you have to do is, say, ranking or some problem like that. What you have to do is you have to first model the problem as an MTP. Okay, you have to find what is the state, agent, environment, what are the state, action, reward, transition. These things have to be clear. Once you model this properly, then you can use the algorithm which are readily available. Say, for example, the deep Q learning algorithm. So deep Q learning algorithm uses deep neural network and Q learning. So this is an advanced algorithm, but the basic work you have to do for applying it is modeling the problem as an MTP and then using the state-of-the-art algorithms which are already existing. So these algorithms like policy gradient, these are already existing algorithms. So you just have to implement that for your particular problem and you can solve the problem. Okay. This is an applied RL research, yes.
Sir, one more thing. Like initially when we started the classical machine learning algorithm, so it was very relevant and many people were able to publish many papers.
Okay.
But nowadays it seems like classical machine learning models are going to be obsolete.
Yes,
so
yes.
What do you think about reinforcement learning? I mean, for how many years it is going to have its bright scope and when it is going to be saturated and all?
Okay, yeah, that is a good question. See, reinforcement learning, historically it started maybe 1980s, late 80s or maybe earlier than that. So it has been there for a long time. It is not new. Reinforcement learning is nothing new. The first book was written in 1996. First edition of the book was in 1996. And the subject was there much before that, from 80s. So it's not new, but if you ask the scope of this, how long this field will be active, really active. So compared to other machine learning, I feel this has more scope. For example, supervised learning, this may have a better scope to do even research in the core RL part, the theoretical part also. But again, if you look for a long time, say 20 years, 30 years, then maybe there is not much scope. But in a relatively shorter time, 10 years, there is scope. That's what I feel.
Okay, sir. Thank you, sir. Thank you very much.
Okay. So any other questions or comments? We have some time, 10 minutes left. So if you have something to ask, we can ask.
Sir, I have a question related to nowadays LLM models, large language models.
Okay.
So, what do you think about its scope and for how many years it is going to be very relevant for us?
One thing about large language models, I did not mention this. Most of the large language models, like which is used in the chat GPT and all, use reinforcement learning. So I forgot to mention that. So thanks for that mentioning that. So large language models, many of them use reinforcement learning. So they use reinforcement learning algorithms. That is one thing. Second thing is how long LLMs will be there. I think they have just started. So there is much more scope again. It is going to be there for some time. That's what I feel.
Okay. Sir, have you done any research paper using this reinforcement learning and all? Any work?
I have worked. So I have worked in reinforcement learning. I have also guided some students. So yes, I have worked. So mostly earlier I used to work on core RL, but nowadays I guide students both M.Tech and also PhD at applying RL to problems. So how to apply RL to different problems. That is what I normally do, not in the core algorithmic aspects.
So working on application area, right?
Application area, yes.
Thank you, sir. Thank you very much.
Yes, thank you. So any other questions? Yes, there is one person who has raised the hand. Garima, yes. And one more person has also raised the hand. So if you have something to ask, you can ask. Okay, if there are no other questions, then we'll stop here. So I think these slides will be available to you. You can check with the TLC. I can share these slides to you. But these are all from the book. There is nothing my own way of presenting, but it is exactly from the book. You can see the book, you will get all the material. Okay.
Sir, can you inform us about tomorrow and day after tomorrow session? Any idea? Saturday and Sunday.
You can contact the TLC, that they will tell you. Okay. So I am not aware of the tomorrow session. So I had only 2 sessions. My sessions are over today. So tomorrow you have to check. I am not sure.
Okay. Thank you, sir. Thank you very much.
Okay.
Thank you very much, sir.
Yeah, thank you. So